Welcome back. In this video we're going to use derivatives. You've learned a lot of rules. We're going to take what you've learned and apply those rules to some simple examples. Have a geological or a geophysical subject in question that needs to be answered. One will be associated with the Earth's circumference, changing its circumference, and the other with the gradient and the acceleration due to gravity. So when we think about the Earth has circumference which is 40 million meters plus some change. And imagine for a moment that you could tie a rope around the Earth of that length, and that you increased its length by 1 meter. Now, if you were to suspend that rope an equal distance above the ground, all the way around the Earth, what would that distance or increase in radius be? So what I'd like for you to do is just think about that. Pause the video, perhaps, and just think about it. Is it a few microns, a few centimeters? If we were to do this on the Sun instead of the Earth, what would that change be? Think about that. Okay, you've thought about that. The expression that we need here is the definition or the mathematical relationship between the circumference and the radius. The circumference is equal to 2 pi r. And so in order to answer that question, we just simply have to evaluate the derivative dc dr, right? So think about that for a minute. What is the derivative of dc dr? dc dr is equal to 2 pi dr. So we're just taking this derivative operator, differentiating this expression. These constants are not functions of the radius. We have 2 pi times dr by dr, which is just 1. So we have a dc, just solving for dc dr is equal to 2 pi. So we have dc is equal to 2 pi dr. And dc is given to us as 1 meter. And so we have that question, okay, what's the change in the radius? The change in the radius is the elevation that rope is going to be suspended all the way around the Earth. And so we solve for dr in this equation. Dr is going to be dc over 2 pi, but dc is equal to 1. So we have dr is equal to 1 over 2 pi, which is just equal to 0.16 meters. Or 16 centimeters. We didn't really need to know what the circumference of the Earth was, did we? So it kind of brings us back to that question of what if it was the Sun, or what if it was an electron? So, what would the change in radius be? So think about that for a moment. Let's use a small p again. An electron, the Moon, the Sun, the solar system. So we're going to tie a thread around the P. We're going to increase its circumference by 1 meter and ask the question, okay, how far above the surface of the P does the thread rest? We're going to center it about the P, and it's going to be perfectly circular, centered about the P. How far above the surface does the thread rest? Well, you got it. dr is just going to be equal to 1 over 2 pi. It's still going to be 0.16 meters. It's going to be 0.16 meters in all cases. Take that rope and stretch it around the Sun, increase its length by 1 meter, and it will float 0.16 meters above the Sun, or above the Moon, or above the electron. In fact, if it's just a dimensionless point, what we're basically saying is, what is the radius of a circle? It has a circumference of 1 meter. That's going to turn out to be 0.16 meters. So something may not, if you check your intuition, what you first thought about that. You may have thought that, well, that 1 meter increase really isn't going to do much. It's that rope is just going to barely float off the ground. But it's going to be 0.16 meters in all cases. So the next question is to take the gradient of the Earth's gravitational acceleration. We know that the force between two masses, m1 and m2, is proportional to their product divided by the distance between them squared. Or, if we just look at one mass like you or me, or the mass of the glass, or the cup of coffee, or whatever's sitting in front of you, we get this mass of that object times g m sub e over r sub e squared. We know from Newton's second law that the force is equal to the mass times the acceleration. And that gives us the acceleration here as just the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. So, to get the gradient of g, in other words, to figure out how g changes with changes in elevation, which are going to be changes in radius, effectively changes in the radius of the Earth. As you walk up the stairs, you're changing your distance from the center of the Earth. You've come up the stairs a certain dr. So we're taking that derivative, d dr, the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. So the question is, evaluate this derivative and rewrite it as a function of g, this quantity here. And while you're thinking about that, just consider why this might be important. And it is important because geologists, geophysicists, they really aren't interested in changes that are associated with changes in elevation. Those changes in elevation really have nothing at all to do with subsurface problems. You may be interested in locating a large cavern, following the axis of an anticline, a fault, the gravitational signature of a salt dome or an igneous intrusion. All these possible applications. So you don't want changes in the elevation influencing your evaluation of that subsurface problem. So you want to get rid of things like changes in elevation, changes associated with surface topographic features, changes associated with the material between you and your datum, sea level, earth and lunar tides, and so on. All these things have nothing at all to do with the subsurface geology. So you want to get rid of them. So let's come back to the problem now. You've evaluated this derivative. These are just constants. So we're taking the derivative of 1 over r sub e squared. And it always helps, at least I find it helpful, to kind of rewrite these denominators, just put them up in the numerator. Makes it easier to apply the power rule. We've got r sub e to the minus 2 power. We take the exponent, we take the power, bring it down in front as a multiplier, times g m sub e, r sub e to the minus 3 power. We reduce this power by 1, from 2 to minus 3, minus 2 to minus 3. We've got the minus 2g m sub e over r sub e cubed. The minus sign tells you that as you increase dr, the acceleration changes. It decreases. So we have a negative sign in there. So part of the problem was to rewrite it in terms of the acceleration due to gravity, g m sub e over r sub e squared, which is g. Well, we pull out one of these r sub e's. We get a minus 2 over r sub e times g m sub e over r sub e squared. You get a dGdr is equal to minus 2 over r times g. We didn't need to know the mass of the Earth. We didn't need to know the gravitational constant. We didn't need to know these numbers. We do need to have an estimate of what the radius of the Earth is. As reiterated over here. So it's a negative because we increase dr, we decrease g, and we don't need to know g or m sub e. We do need to know g and r. So taking a look at what that value would be, substituting for the radius of the Earth of 6.37 times 10 to the 6th meters, and g of 9.8 meters per second squared, we get dGdr is equal to minus 0.000003077 meters per second squared. I should have put per meter in there. This is dGdr. So this would be 3.08 times 10 to the minus 6 meters per second squared per meter. And I've got it over here. I've just left it in this decimal form. We typically write it as 3.08 times 10 to the minus 6 meters per second squared per meter. So if we increase the distance from the center of the Earth by 1 meter, then dg, we're multiplying both sides by dr. dg is equal to minus 0.000003077 dr, which has units of meters, which I didn't put in there. But our result is in meters per second squared. The meters cancel out. And since dr is equal to 1 meter, we just have the change. For every meter you go up 3 to 4 steps on the staircase, the acceleration due to gravity drops by 3.077 times 10 to the minus 6 meters per second squared. You say, well, that's so small. Who cares? Well, modern day gravimeters can measure these kinds of changes. Very often, the subsurface features that you're looking at may produce very small anomalies. So being able to get rid of changes in the acceleration that are associated with changes in elevation can be very critical. It depends on it does depend on the scale of the feature that you're looking for. Maybe an error of about a meter or two in your elevation would not be a big problem in some cases. In other cases, it might mask the anomaly that you're looking for entirely. Well, this effect here is associated with a change in the distance from the center of the Earth, or a change in dr. And it's referred to as the free air effect. It really does nothing else but compensate or describe the influence of how g changes as you change your elevation. It doesn't compensate for anything else. It doesn't compensate for hills and valleys. It doesn't compensate for the lunar and solar tides, for example. Just the change in the elevation. So small but significant when you're working with gravity data. And we'll probably have some problems later on. We'll talk a little bit more about this. But for next time, we're going to talk a little bit about applications of derivatives for flow volume estimation and seismic illumination, or seismic intensity. So see you next time.